The Newton's polynomial you can see here is actually similar to the Taylor series expansion, if you remember from the earlier chapters. It has the first function, for instance, and finite difference here is this times h. H is basically the difference. And for the second term, we have the second finite difference. It's this, and the second two times differences, etc. So it's very similar. That's why when we truncate this and this, the errors will be in the same magnitude. So we can use a similar idea as the Taylor series to be able to predict the error of the Newton's interpolation. And again, if you remember from the Taylor series, the error was like this. When we truncate from a certain order, for example, nth order, there is an n plus 1 order finite the derivative actually. This derivative is the same for the interpolation as well. And this part is these differences, and also n plus 1 factorial is here as well. So it's the same idea, just these differences are differences of the data point that we want to find the results and the actual input points that we have as the data. So this is basically the truncation error for the Newton's interpolation. And we can have an alternative formulation that uses finite divided difference approximate. Basically for this one, we will use finite divided differences. And Rn is, these are the finite divided differences here, this part. And these are this data again. And it has the unknown fx here, this fx, because x is not known. Actually, x is known, but fx we want to find it because x is the data that we want to find the fx value. If a known fxn plus 1 is available, so if we have another data, an additional data n plus 1, then it can be used to estimate the error as well. So because we don't know fx, from here we are not able to get an error value. But if we have additional data fxn plus 1, instead of using x, we can use that here to predict the estimate. That's the simple idea actually. From here, even before calculating the interpolation, we can have an estimate of the truncation error. Let's check this in an example. Before showing an example for the truncation error for the Newton's polynomial, we will continue on the error estimation because we said that we actually added an additional term or any additional data, n plus 1 data, to be able to predict the truncation error. So the increment added to the nth order case to create an n plus 1 order case is interpreted as an estimate of the nth order error. So basically we will have n plus 1 order case actually, but we will just use an nth order polynomial. Then we use the additional data to predict the error. So here the actual error was this, as we said, but we have x here that for which we don't know fx value. So we are not able to use this. Instead, we will use this additional data, xn plus 1, that we know, for which we know the function value. We use that as an estimate for this, basically. And here, that's why we have this for Rn, and for this for Rn plus 1 actually, or n plus 1th order case. So f function n plus 1x minus f function n. The difference between them gives us Rn, and fn plus 1 is fn plus Rn. So that's why the nth order prediction should be much closer to the true value than the nth order prediction, because we have an additional data. That's why Rn equals the subtraction between n plus 1 function value and n is expected. So, however, up to this chapter we learned that the error was present minus previous. But here we see that we have a future data. So this is an additional data. So for interpolation we have error is equivalent to future minus present. This means, the future minus present means that for a series that is converging rapidly, the error estimate could be less than the true error. So you can see that in the next example, but because we are using a future prediction or future data in the prediction of error, the error will be less than the true error actually. The higher order interpolating polynomials are highly sensitive to data errors, and this is called ill-conditioned, and the error equation will be much more sensitive because we are using the future data. This error equation will be much more sensitive to the data errors, and therefore it's better to use it just for exploratory data analysis, for which Newton's polynomial is best suited. So rather than saying that, okay, this is definitely our error, we shouldn't say this. We should say that, okay, let's try an nth order, n+1 order, or n-1 order polynomials, and check we can compare them for exploratory purposes, just data analysis, using this error prediction function, using the n+1's data, actually the future data. Here we continue on our example. In 15.1, 15.2, 15.3 we solved for first, second, and third order Newton's polynomials, and we will now have the error estimation in this example 15.4 for the same problem. And if you remember, the problem was using the function of ln, or logarithm, natural logarithm, to find the values. And here we will estimate the error for the second order polynomial interpolation of example 15.2, and we will use an additional point of 5 actually, and we know that this is this value, but we are not using this in the second order polynomial. For the second order polynomial we will have x0, x1, x2 as the 1, 4, and 6 actually, and this is an additional data, and the estimate was this 0.56 in 15.2. Let's remember that first, and the true value is this 0.69, and the error is basically just the subtraction of these, the true error, not the percentage error or relative error, this is just subtraction, is this value. So let's say we didn't know this true value, we don't know this one, and so we are not able to calculate this, but we can have an estimated error by using the additional data point. So future minus present we will make. For that we will use this truncation error with the n+1 data point, which is this new data, and for that we will apply this for 3 data, because we have second order, we have 2, 2, 1, 0, we have these data anyway, and 3 as this one. And when we calculate this finite difference value or function, we actually calculated this in example 15.3. This becomes the third order anyway, because we have the additional data. And these for x0, x1, x2, which are 1, 4, and 6. When you multiply them, for x equals 2, when we write 2 here, the error will be around 0.06 according to this estimation. And you can see that this is much lower than the actual true error, let's say, as expected, but the orders are similar, so it's in between 1 and 0, let's say, and closer to 0. This is also closer to 0. Of course, there is a like half, this is half of this, but still same order of magnitude, but this is smaller. So because we don't know this, because we don't know the true value, we can have this estimate and say that, okay, our error will be in the magnitude of this, so this is not bad, we can say, maybe, or maybe a little bit higher from this, we can say 0.1. So this is just an exploratory analysis, that as we said in the previous slide, it's just for making interpretations. We cannot say that, okay, this is our actual error. No, it is just an estimation, but we can see the order of magnitude by using this. So this was an example for error estimation for the Newton's interpolation. We can write a computer code for the Newton's interpolation, and you can see the algorithm here. For that, you can simply use this in MATLAB, for instance. Remember that our function is this for Newton's interpolation function, and we need to determine the coefficients, which are the finite divided differences. And here you can see the first finite divided difference was just the first value of the function value. Y is the function value, x are the data inputs, let's say, and xi is the start point, or not the start, but the point that for which we wanted to calculate the y value or the function value. And this is the approximation error that we want to use to check the error. So here in this for loop, we will have the finite divided differences, you can see, and we will use them for each data. Then we will implement it for calculating x terms, like here, and subtractions and x term, and y interpolation value is this. Basically, this formula is used here, and the error is between the interpolation of 2 by adding one additional data. This is just an approximation, and if this approximation is smaller than this, for example, we can say this is a good value, then we can use this simply as the interpolation point, or as the interpolation prediction, let's say. So it determines the coefficients and determines the predictions and associated error. So let's check the usable properties of Newton's interpolation. By adding terms, higher orders can be simply used for interpolation in the same program. We can add these terms over here to increase the order of the function, Newton's function, used in the interpolation. This is valuable, especially if the order of data curve is not known. So we add the order and see the approximation error results. If it is getting smaller, and maybe after some point it will increase again, then at that point we will stop. And maybe with a threshold we will stop. And the algorithm on the left side allows for efficient computation of finite differences at higher order using the ones at the lower order. So we are using the lower orders and we are adding them to get the higher order values by using this for loop actually. And the error estimate is simple to incorporate into the computer algorithm. We said that we add an additional point to get the estimate of the error over here. So we will have this addition point to calculate finite divided difference, basically. Now you can use this algorithm to create a MATLAB code, for instance, and use it for your interpolation problems. We have a final example for this chapter, and this is for using the algorithm, computer algorithm for interpolation, Newton's interpolation. And we will interpret the results of different order of interpolation polynomials that we fit to the data. So the data is here. We actually, in the previous examples, we use these for data, and we will add these as well. Now, when we add these, we have a pretty much large data that we can increase the order of the polynomial to fit. We start from the first 0th order up to the 5th and 6th order actually. This is the order of the function, and this is the error values. And interpolation for x equals 2, and the orders are here, affects function values, and up to 7 you can see the errors, the function values are getting converged to 0.69, which was the true error actually, it's true value actually, if you remember, and the error is getting smaller and smaller. And when we plot the true error, you can see the 5th order, especially here, 69, 6th especially, gives the very small values of errors, so it's getting smaller, true error. The estimated error is calculated by using the additional data. So for example, for the first order we use this data, but for the estimation we also added this data to get the first order, this value. For the third order we use these 3 data for interpolation, and we use this 4th data to calculate the truncation error Rn by using the formulation we mentioned in the previous slides for a prediction. You can see it's here. So for all we did the same. We used a later term or later data for estimated error, and you can see that the estimated errors are smaller than the true error, as we said earlier. And this is a general actually rule of thumb, we can say, because we are using a future data. It gives us a smaller value, but the magnitudes are similar, so, and the behavior is similar as well. So after the 5th order, the error is the same for both. So we can say that we can use estimated error as well for investigating the quality of the predictions when we increase the order. And for example, after 5 we will stop. At 6, for instance, we can stop, we can say. So estimated error and true error are similar. Their agreement improves as the order increases, as we said here. Also, the positioning and ordering of the points are important. So if you see, we don't have an order of the data here. And up to the 3rd order, we use actually these 3 or 4 data. We have 4, 6, and 5 values. And these are distant from x equals 2. So these are like distant values from 2. That's why we have actually a large error over here. But the fourth order has better improvement because x equals 3, this one is added, which is closer to 2 value, the x equals 2. That's why it gives a good result. After fourth order, we see that it's decreasing because we have closer data to x equals 2 for which we want to find the function value. Which means that when we add data points closer to the point for which we want to find the function, we will have better approximation, better accuracy. And we can see that when we use a reverse order of the data for interpolation. And this lower data or lower function error demonstrations are for the interpolation with a reverse order. So for zeroth, we used only this. For the first order, we used only 3.5, 2.5, this. And because this 2.5 is very close to 2, we have a better error, a lower error, closer to 0, compared to this one, in which 4 is far away from 2. And similarly, for third order, you can see that we have almost like 0 error. And for the third order, what we have? We have 1.5, which is very close to 2 as well. So 2.5, 1.5 are very close to 2, closer than these 6, 4, and 1 that we used here. That's why this error is much smaller than the error of this one that we use these data. So when the order is reversed, the points are closer to and space on either side of ln2, the 2 value actually. That's why the errors are getting smaller, very small, near 0 at an earlier order. At third order, fourth order is much better when we have a reverse order. So the ordering of the data is important. That's why you can change the order and try interpolation again to see if you have a better approximation of the results in your problems. For example, by the second order, the error reduced less than 2% here, second order, which is very good actually. You don't need to use higher orders when you have a reverse order of this, for instance. You can have an order of like increasing of data and try that as well by yourself. You can write your own MATLAB code and try this and see how the results go. This is the end of chapter 15, and we learned about Newton's interpolation polynomials in this chapter. And this is actually chapter 18 and section 18.1 in your book. And you can read this chapter to have further information about Newton's interpolation polynomials. Thank you very much for listening, and see you in other classes.